what we're doing in quantum computing, as well as some amazing work we've been doing with many of our partners. And in fact, you'll have the chance to hear talks from and ask questions of many of our partners in the schedule of today's Quantum Day. Now, the goal of this introductory session is just to kind of let you know what's going to happen, give you the lowdown about how it all works. And also, I thought before we do that, have a chance to kind of step back and put into context how incredible some of the work we're going to see today is. We hear an awful lot about all the potential application areas where quantum computing might have an impact. Things like drug discovery, materials development, and even things beyond that. But I think it's always good just to take a minute, step back and nerd out and actually think about what we're really doing when we build quantum processors, because our partners are doing some amazing work in building chips that can manipulate individual qubits. And for many approaches to building quantum computing, that means manipulating individual atoms. And so I think it's worth reminding ourselves just how incredible that is. And to do that, I've got with me an apple. Now, this apple is going to help me help you remember just how incredible quantum processors are by remembering just how hard it is to work with individual atoms. And to do that, I want to do a little thought experiment. I want us to imagine what would happen if we could keep zooming into this apple and what we would see. But to make things perhaps a bit easier, let's instead flip it around and suppose that we could expand this apple and everything inside it, and we can start to imagine at what point would it start to become big enough that we could see and kind of maybe even pick up more and more interesting smaller things inside it. So the first thing that would happen if you could expand this apple, the first interesting thing you'd start to see would happen when this apple became about as big as a pretty big building. So this is NVIDIA headquarters in Santa Clara, California in the USA. And if we made this apple about half as big as our NVIDIA headquarters so it could sit on top of it, then you would just start to begin to see the individual biological cells inside that apple. You'd be able to pick one up and you'd be able to start look at it and to kind of manipulate it. But we want to go beyond that. If we're interested in quantum computing, we need to make the apple even bigger. If you carried on expanding it, then once the apple was about the size that it would sit on top of New York, which the irony is not lost on me that is conventionally the Big Apple. If you could sit on New York and go most of the way to Philadelphia, then you'd have an apple that was big enough that if you look closely, you just about start to see proteins, the small molecular machines that work inside the biological cells and perform all the miraculous things that we see happen in biology. But if we want to do quantum computing, we need to go even smaller. We need to make the apple even bigger. And in fact, if you were to continue to expand this apple, then eventually you would make it big enough that you could pick up and start to manipulate and see the individual atoms that make up the apple, that make up those proteins, that make up those biological cells. But to do that, you would need to expand this apple to be the size of the whole planet Earth. In other words, what I'm saying is, if you as a human wanted to be able to manipulate individual atoms, the things that we often use to build qubits, you would need to take something like an apple and expand it to the size of the whole Earth, just to even be able to start to see and manipulate those atoms. And so now if you shrink that all back down to the size of the apple, you can start to begin to understand just how incredible quantum processors are, that they can take individual ones of those atoms and control them very delicately and manipulate them to help us do quantum computing. Okay, I've taken the liberty of letting myself go off on a bit of a physics rant there. So this is the idea of quantum computing. We can control individual quantum objects, and doing that lets us solve incredible new problems. And that's why NVIDIA is so interested in quantum computing. NVIDIA has a long history of trying to change what we can do with compute. And now that we're beginning to have the ability to manipulate quantum objects with this level of sophistication, it opens up the possibility that we can begin to think of a whole new kind of computing, quantum computing. And quantum computing, with its possibility of changing how we think about things like drug discovery, materials science, even things like designing new batteries, new electric vehicle battery chemistry, Quantum computing will work in concert with existing supercomputers to allow us to really change the application areas where we think supercomputing can have a huge impact. And so from NVIDIA's point of view, it really makes sense for us to be fascinated and interested in and accelerating quantum computing, because it does what we've always done, which is to expand the areas in which computing can have a dramatic effect. And in fact, if you want a vision for how quantum computing will look in the future when it becomes truly useful, when it starts solving problems that really have huge societal, financial, or scientific impact, then I think that the whole kind of community is now beginning to come into broad agreement that the device that will look like isn't something all that esoteric. It'll be a supercomputing center in the kind of way that we know it today. But alongside those racks that we're so used to, full of GPUs, there will also be a new kind of hardware, the quantum processors, which will be called upon with a very close connection between the supercomputer, the GPU supercomputer, and that quantum hardware to perform certain parts of a computation that are just beyond or outside of the scope of conventional GPU supercomputing. There's also another reason, by the way, you need quantum processors to be so closely connected to conventional supercomputers, and that's to run them at all. As you can imagine, trying to manipulate things on the scale of atoms or other complex systems like that is very, very demanding, and the control tasks you need to do to make that happen really require GPU supercomputing. So at NVIDIA, our vision for the future of quantum computing is one where all kinds of quantum processors are very closely connected to GPU supercomputing hardware, both to control and run those processors, but also so you can have a hybrid quantum classical system that can start to perform supercomputing tasks beyond what we can do today. And so at NVIDIA, we're doing everything we can to make this future of quantum GPU supercomputing arrive as quickly as possible. But we're not doing that by building quantum hardware. At NVIDIA, we don't build qubits. We don't build quantum processors. Many of our partners are doing incredible work in that respect. But at NVIDIA, we're instead building a platform that draws on accelerated computing and brings quantum developers the tools, the GPU supercomputing that they need to turn the qubits that they have into hybrid quantum GPU supercomputers. Now, you'll hear more about this platform that we're building in our special address, which is the next session coming after this one. But one particular tool that's worth pulling out from that platform and mentioning here is AI. Generative models and other state-of-the-art developments in AI are really creating an inflection point in quantum computing developments. And this year is already seeing a dramatic new set of breakthroughs that have been enabled by quantum researchers and developers using AI, both to build quantum hardware, the processors, but also to build the applications that they will want to run on hybrid quantum classical systems. And the importance of AI is really reflected in our schedule for today's Quantum Day. You'll see that quite a few of our talks are focused around AI. So before we start on this program and we get to the meaty details and you get to hear the experts tell you about all the latest, I thought it would be helpful just to summarize the schedule and let you also know how the talks are going to work. As I previously mentioned, our next session after this one at 8:15 a.m. Pacific time will be from NVIDIA, from our VP of Applied Research for Quantum Computing, Christos Vore, who's going to be giving us the Quantum Special Address. Now, in this, you'll not only learn more about the things I've mentioned already, the platform that NVIDIA is building for quantum computing, but excitingly, there'll also be some new announcements that won't have been made anywhere else before here today. Then at 9 a.m, we'll have a talk from Juha Vartiainen at IQM, who's going to be telling us about a very interesting application of AI that quantum developers have been exploring for calibrating quantum processors. At 9:45 a.m, we'll hear from both Chris Chamberlain at NVIDIA and also Joan Camps at Riverlane. And they'll be talking about another application of AI in quantum computing research, specifically for quantum error correction. Now, if you've read about the latest developments in quantum computing before, you will not have failed have heard about quantum error correction. There's wide alignment across the community that to build a large, useful quantum computer, you really need to crack the challenge of quantum error correction. Techniques that allow you to kind of continually fight against the fundamental noise that qubits experience. And so it's especially exciting to hear that there'll be uses of AI that might transform progress in that area. And so that's a great talk to look out for. Then at 10:30, we'll hear from Stephen Clark at Quantinium about yet another application of AI in quantum computing work. And this time, rather than it being for how we calibrate quantum processors or perform quantum error correction on them on the hardware side, we'll be hearing instead how AI is really making huge advances in how we develop the applications that we will want to run on that hardware. And this is really important for at least two reasons. First of all, we'd love to discover more applications that will run on a quantum computer much better than on a normal conventional computer. And so it's especially exciting that AI might help with that. But also, if we can find ways to use AI to make existing quantum applications more efficient, more optimal, then we might be able to run them on earlier generation quantum hardware. So if you want to get to useful quantum applications more quickly, there's two ways you can do that. You can make the hardware better more quickly, but you can also make the applications you want to run require, less advanced hardware. And so this will also be an interesting one to look out for, to learn what the state of the art in AI for quantum applications are. And then the final talk that we have today, the penultimate talk that we have today, 11:15 a.m., is from Yaniv Kerman at Quantum Machines. And we've talked a lot in this introduction about how a vision for quantum computing is integrating quantum processors with GPU supercomputers. Yaniv is going to talk to us about how you actually go about making that connection, the challenges involved in that, and how people are overcoming them. And then finally, at 12 p.m., we'll hear from Stephen Frankel at Technion. He's going to talk to us about some extremely interesting work they've been doing using NVIDIA's DGX Spark, which is a small desktop supercomputing system that they've been finding that they can use in quantum research. And a lot of researchers around the world have been adopting DGX Spark, both to accelerate work they've been doing on applications or simulating quantum computing, but also actually connecting them to qubits to start to do kind of prototyping about how quantum GPU supercomputing and the interconnects it involves will actually work. And that's our schedule for Quantum Day. In each of those sessions, there'll be a talk from the speaker, and then there'll be about 15 minutes for live Q&A. So please use the software to post your questions. We obviously won't necessarily have time to go through all of them, but we'll try and have the speakers answer as many as they possibly can. So please take this unique opportunity to speak to these leaders in the field and ask them your questions. We also have some resources here for you. So after this session, after Quantum Day, if you want to learn more about what NVIDIA is doing in quantum computing, I've posted a few links. The top one takes you to our main NVIDIA Quantum page, which is in some sense the hub from which you can connect to many of the other things we're doing and many of the other products that we're releasing to build this platform for hybrid quantum classical supercomputing. And then further down, I've got a few more links which give you direct access to some resources with maybe some of the key parts of our platform. So CUDA-Q is our software platform that lets developers start to program systems that include both quantum processors and GPUs and CPUs. And so there's some links there to how you can get started if you're interested in exploring quantum computing. There's also a lot of resources there to use that software development environment to also learn about quantum computing from scratch. We have something called CUDA-Q Academic, a series of tutorials and lessons that can help you do that. And then also I've put a link to our CUDA-QX, QEC and Solver libraries. So if you are someone doing quantum computing research, these are kinds of tools, these are libraries that help you very quickly get started on some of the most important problems in quantum computing with CUDA-Q, like quantum error correction. So I hope you enjoy the rest of the day. We're really excited to have you here and look forwards to giving you the rest of our talks. Have a great Quantum Day.
All right, everybody, thank you so much for being here. I think this is going to be a good one. I have no idea what they're announcing, but should be good. Testing. Yeah, it looks like this is working. Yeah, his team reached out from Diary of a CEO. I don't know. I did not believe it at first, but I think they have a very large outreach team. So somehow, somewhere, somebody mentioned my name. So I'm sure I'm not the number one person, but I am in their sort of pipeline of people that maybe if we can arrange it, because I think he's got an office in L.A., he's got one in New York. And I guess this week he's in New York. I don't know if I'm supposed to be saying this actually. Maybe I should just be quiet about this stuff. Um, he's a little bit too corporate. Somebody's saying, I like, yeah, I mean, he's a business guy, I guess, but he's, I like how he interviews. He's very smart, and he's able to get people to open up and really talk about.
Really opened the door
Oh,
to
whoops.
molecular science and ultimately modern medicine as we know it today. Now, quantum computing has a similar capability, right? A similar potential where it has the ability to reveal things about the world that we cannot understand today without it. It has the ability to reveal quantum scale interactions for things like chemistry and material science, to enable things like drug design, energy breakthroughs, and I think quite excitingly, areas that we haven't quite discovered yet, right? That hopefully all of you across the world, across the community can help identify, what will you do with this amazing new scientific instrument? But to really get to the point where we see valuable scientific discovery, we need to convert, qubits into a quantum computer and ultimately into a quantum GPU supercomputer. And to do that, it requires combining, bringing together, integrating artificial intelligence with accelerated computing, with quantum computing, with AI supercomputers. And so it's a very exciting time to be alive, quite frankly, right? Where we have this convergence of artificial intelligence and quantum computing coming together. And it has the opportunity to reveal things about our world that we've never known before, and to speed up computation that we may not have thought possible. Now, quantum computers will unlock, such new applications when they come in the form of quantum GPU supercomputers, right? It will help improve everything from, things like drug discovery, potentially to solving things in the space of energy breakthroughs, electric vehicle chemistry, new materials that may have properties that weren't thought possible. Um, but I think, most excitingly, as I mentioned, it's the things we haven't thought of yet that quantum computing has the potential to reveal. And to get there, we need to make it into a working system, a computational system that can reveal these new things about our world. Now, really, to get there, we need to not only make it a working system, that system has to be reliable and it has to be scalable. We like to say it needs to be fault tolerant, right? It needs to be able to tolerate faults, to tolerate errors. Sometimes we call it noise, right? And continue to enable a reliable computation. So it's now, broadly agreed upon across the community that we will require what we call logical qubits. This form of qubits, it's like a virtual qubit made up of many, several to many physical qubits. And these logical qubits will undergo what we call error correction, right? Quantum error correction, where we can learn what kind of things, right? What kind of noise is happening on these qubits to achieve longer and bigger computations, right? So we can help prevent the faults, prevent the noise as we compute. Ultimately, we want to scale to longer, more complex computation because it's in that realm, right, when we have more logical qubits and more computation available at our fingertips, that we can expand the space of possibility for scientific discovery and applications. And this year, 2026, will no doubt witness both the scaling up of logical qubits and, importantly, the integration of those logical qubits into a computational system, right? A system that's complete with GPUs for qubit data processing, inference, and decoding. And so the challenge ahead of us is not just counting logical qubits, right? Of course, it's important to have more logical qubits over time, but it's also a system engineering challenge around engineering a system that can come together to enable programming applications for scientific discovery and beyond. Now at NVIDIA, we think a lot about how to enable the community, the ecosystem, to program such a system and build such a system. And ultimately, right, we want to build this into a quantum GPU supercomputer. And so for this, we've introduced an open quantum platform. And in our NVIDIA open quantum platform, we offer tools and a platform to enable researchers, scientists, builders, and engineers to address the challenges in developing and running hybrid quantum classical systems. So with CUDA-Q, we offer an open source software platform that enables developing for and operating a hybrid quantum classical system, right? It enables programming those applications that will lead to the discoveries of tomorrow. And with cuQuantum, we offer the ability to speed up simulations, right? So that you can test your ideas, design new capabilities, everything from simulating device level physics all the way up to large scale quantum error correction and full state simulation of your application itself. And then with MVQ Link, we offer quantum GPU integration, a reference architecture, an open reference architecture that enables low latency integration of a real-time host, right, complete with GPUs with your QPU, right, to enable that tight integration and the ability to enable calibration and decoding of your quantum system in real time. And we'll talk a lot more about that application, decoding and calibration today. Now, ultimately, we need to go from today's quantum systems, which are limited in the number of logical qubits, all the way to a scaled quantum GPU supercomputer. And when we look at what it takes to get there, it turns out that many of the tasks that we have in front of us, the challenges we have in front of us to close the gap between today's system and the quantum GPU supercomputers we envision, it's ultimately AI, right? These tasks ultimately can be enabled with AI. And so the types of tasks that we need to address include everything from what we call decoding, that's understanding the type of noise in the system and inferring better corrections to the system in real time while computing. We have to be able to calibrate, right? Bring up, calibrate, and tune the qubits in the QPU itself. We need to be able to develop applications that are hybrid, that know what are the best things to do on your classical resources, right? Your GPU, your CPU, your LPU, right? And what are the best things to do on your QPU? And then ultimately, we also want to be able to model the system in detail as it's running, but also offline to enable better extreme co-design scenarios where we can co-design the application with the error correction and the quantum plane. And we also want to be able to generate data that mimics the quantum system at various levels so that we can train new AI models to address different tasks across the system now and into the future. Now, all of these tasks can in fact be sped up and enabled with AI models. And we'll talk more about that today. So AI is truly a transformative tool for quantum computing. And we can say that quantum workloads ultimately are AI workloads, right? These tasks that we have in front of us for quantum computing are ultimately AI workloads themselves. But what's still missing in this is open models, right? Open models, open data sets, open weights that enable the community to build on, fine tune, and improve upon. Now, across other fields, open source AI is really the key to driving innovation. you can call it a backbone of innovation. And it's seen quite an uptake in recent years, right? We're now seeing almost 3 million open models. Over 60% of companies are using these open models. And you can see that there's just an explosion in the number of uses of open models. Now, in quantum computing, open models could be especially important. We have a diverse number of qubits, a diverse number of quantum error correcting codes, diverse set of applications, right? So many different approaches here across the stack. And having access to models and data could really make a difference for researchers and developers worldwide. Right now, today, most of the data in our field in the ecosystem is proprietary. Open models change this, right? It enables everyone to participate, everyone to advance and accelerate towards useful quantum computers, right? Open models for quantum computing enable fine-tuning for a qubit type, right? Fine-tuning for a specific error correcting code, right? Enables accessing open data sets and open benchmarks as well. And so, the desire for open models for quantum computing is huge, right? The ability to have access to open models and data could really change and transform the path to useful quantum computing. And that's why today I'm thrilled to be sharing that we are announcing NVIDIA Ising, the world's first family of open models to accelerate the path to useful quantum computers. Now, this is really an open platform that all QPU builders and developers can extend, can build on. It's about providing open access, fine-tuning, and also enabling data sovereignty, right? You can use these models and run them locally, fine-tune them locally with your own data. And ultimately, these models offer leading performance, in particular for QPU calibration and decoding, which I'll share more on. And they scale not only for today's quantum systems, today's QPUs, but they also scale all the way over to quantum GPU supercomputers of the future. These models today that we're releasing are really focused on building better qubits, enabling reliable QPUs, right? And so the two models in particular in the NVIDIA Ising open model family are Ising calibration and Ising decoding. Now, these two tasks in particular are incredibly important for quantum computing today, right? These can mean a difference in a quantum computer being able to run more operations reliably, to be able to handle larger compute, and ultimately to even enable more logical qubits that operate that operate better than the physical qubits themselves. So with Ising calibration and Ising decoding, we're offering open models and open data for two very critical problems in quantum computing today. And they come not only with the models, but also with cookbooks, right? With workflows for training, fine-tuning, quantizing, and performing that inference, right? So many different workflows that you can use for your custom task. And it enables researchers, developers to really build on these models, right? You can take them and extend them for the tasks in your quantum system or QPU environment. It's also open research, right? We are also pushing out papers on both the Ising decoding and the QC eval benchmark. And there are also open data sets supporting these open models. So we're releasing both benchmark data and training so that you can extend, fine-tune, and also train models yourself. Let's talk more about Ising calibration and Ising decoding, right? These models also are already used by members across the ecosystem. You can see that there are a large number of QPU builders, quantum system developers, researchers across our ecosystem using Ising calibration and Ising decoding already today. Now, these models in particular, as I mentioned, really zoom in on two important tasks on the path from today's systems to the quantum GPU supercomputers of tomorrow. And so NVIDIA Ising today includes open models for both QPU calibration and decoding, right, for quantum error correction. let's talk about these two, right? Why is this important? It's because quantum computers have noisy qubits today, right? These are two key workloads that really enable addressing noise in a quantum computer, right? When we think about a quantum computer, kind of like running a piece, playing a piece of music, right? Over time, that music becomes very noisy in a quantum system today. And to combat that noise in the quantum system, we really have to address how we calibrate, tune, and really bring up or instantiate those qubits. And we also have to make sure that we can continue to calibrate those qubits as they're being used in a computation. And that involves both calibration and decoding. Decoding being how we use information about the noise in the system and then work to apply a correction. And so both of these tasks we can address with open models that we're offering in the NVIDIA Ising open model family. So let's look at the first task, calibration, right? In the task of calibration, ultimately you have a lot of data coming at you, right? A lot of data that you have to understand about your qubits, the environment, how to tune or tweak the QPU, and there are many parameters. And depending on your type of qubit, the parameters and the kind of the knobs that you have at your fingertips to tune, they can be very different, right? And so, tuning one qubit may look very different than tuning another type of qubit. But you can see that there's a lot of different signals that you have and that you have to then really keep within the operational values to enable a qubit to be reliable and stable and useful for computation. And so when we think about taming the QPU, it's really about enabling calibration while you're performing quantum computation, right? You need to calibrate as you turn that QPU on, right? Turn on the quantum computer, and then as you run and execute on the QPU. And today, calibration of the QPU and of the qubits in that QPU is very complex, and it's mostly handled by humans. And when I say that, I mean it's mostly manual, right? It's often a manual process, many steps in the process, and sometimes there are very simple algorithms in the loop, but it can be a lot of decision points, right? A very complex graph, as you see as an example here, on going from turning on those qubits, right, and calibrating those qubits to ensuring they're operational during a computation. So often a manual process today that's complex and time consuming. Ultimately, we want QPUs to be able to run in an automated fashion and ultimately as part of a quantum GPU supercomputer. And so we need to automate this task and not only automate it, but make it more reliable and more efficient. And so with NVIDIA Ising calibration, we have an open model, and it's really a customized VLM, a vision language model. And it's able to recognize results from experimental data and from experimental plots, for example, and then infer the correct and improved calibrations that are required to stabilize that parameter or that qubit within the QPU. So this is a 35 billion parameter model we've used here, and it also comes with an agentic workflow to automatically calibrate the QPU. It's QPU agnostic, so this can be used with many types of QPUs, but at the same time, it's qubit performance, so it can be tuned to the type of qubit that might be considered, right, that you're applying this agentic workflow to. And we find it outperforms any other model for calibration. So it's beating both open and closed models in the calibration task. NVIDIA Ising calibration, what we see in terms of size is we can achieve this 35 billion parameter model can be up to 15 times smaller than alternatives. So it can be easily trained and also scales for calibrating for larger and larger systems of qubits. And in addition, it's locally deployable, which is a real need for a QPU, a working QPU system. In terms of speed, we see that it allows calibration to be conducted in a much shorter time frame compared to the current manual, human intervention alternatives. And in terms of performance, it is the world's best for the calibration task. We can reliably infer calibration actions from very complex data, and it outperforms any other AI model today. Now to calibrate, right, to benchmark our calibration model, we are also introducing an open benchmark we call QCal-eval. There was no benchmark previously for calibration that really captured the broad complexity of calibrating a QPU. So we ultimately created one with partners, right? With over 20 quantum partners, we created a new benchmark, QCal-eval, and it measures an aggregate performance across 6 key tasks that you can see here that are part of calibrating a QPU based on data coming from the QPU. The scoring is out of 100 points. And to build this benchmark, we worked with 7 different QPU builders on data, right, on providing data from different types, right, from different types of qubits, different types of QPUs. We bring that data together, and these QPU builders generously offered their data for this open data set and this open benchmark. So we bring together data from a variety of QPUs. And again, this benchmark has been validated from over 20 quantum partners across the quantum computing community and industry. When we look at performance of NVIDIA Ising calibration on QC-eval, we can see that it outperforms all other models, including those, such as Gemini, Claude Opus, and GPT 5.4. So you can see that for the task of calibration, NVIDIA Ising calibration model outperforms all others. And what's exciting is it's already deployed and being used by a variety of partners across the ecosystem. So academia Sinica was able to do readout calibration of a full superconducting chip in 30 seconds. This task typically would take a human expert around an hour. So we're going from an hour to just 30 seconds using the NVIDIA Ising calibration open model. And for a new engineer, the same task may take up to half a day. So this enables, right, a very substantial decrease in the time to do readout calibration of their superconducting chip. With conductor quantum, we were able to isolate a single electron on an ERO-Q electrons on helium chip in just a few seconds with the Ising calibration agent. And previously, this task was done manually. So you can see already today, Ising calibration is helping calibrate quantum chips around the world and offering substantial improvements and automated calibration. Now let's turn to decoding, right? Another challenge for quantum computing and scaling up quantum computers, right? Qubits are inherently noisy, and ultimately these qubits, when they're noisy, right, they cause errors in the computation itself. Now, what we want to be able to do is extract information about those errors, about that type of noise, extract that information, and this is extracted as classical bits. Ultimately, we can then take those classical bits and we can run a classical algorithm, right? What we call a decoding algorithm on those classical bits and infer the best possible correction and then send back that information to the quantum computer. And so we really do have a round trip, extracting data from the quantum computer about the noise, running a classical algorithm to learn how do we correct for that noise, and then sending that signal back to the quantum computer. Now, this is known as the decoding problem, and we need to be able to do this while we compute. We need to do it in extremely low latency, and we have to do it, very fast with high throughput and low latency while the QPU is running. Now, to make this problem easier, or in some sense faster, what we can do is we can first process those classical bits that are coming from the quantum computer about the noise. We call these noise syndromes. We can first process that using what we call a predecoder. And this results then in, fewer residual noisy syndromes. And ultimately, by using this kind of fast filtering or fast processing using a predecoder, we are able to speed up overall the decoding process. And so today, we are announcing NVIDIA Ising decoding, an open model for this predecoding problem. This is adaptable also to any QPU or any decoder, and it offers scalable real-time inference. And so this can be used in real-time computation for your QPU. It enables both local and parallel error correction at low latency. And in addition to offering this open model, it can also be used, right? There's also a noise learning architecture that comes with it that enables learning qubit noise from real experimental data. Now, NVIDIA Ising decoding is 2.5 times faster than alternatives today. It offers 3 times more accuracy, so 3 times better logical error rate, and it offers 10 times less training data required to train such a model. Now let's look at the details a little more. With NVIDIA Ising decoding, we've measured 0.1 microsecond latency per round for decoding. We offer 2 open models here as part of NVIDIA Ising decoding. One is tuned for fast decoding, and another has been tuned for accurate decoding. The fast decoder has just around 1 million parameters, and again, it's optimized for low latency scenarios. And here we see a 2.5 times speed up of the decoder as compared to other standard alternatives. On the Ising decoder, in terms of the Ising decoding accurate model, we can see 3 times improved logical error rate. And so that model is very much tuned for accuracy. Now, both of these are already being used today by different partners across the ecosystem, and you can see those partners at the bottom of the slide. But in particular, I want to call out Inflection, and Inflection has integrated the predecoder with an open source framework called Leaky, and they're using it to model the effect of leakage effects in different quantum error correction workflows. And by using the NVIDIA Ising decoding model, they're seeing a 2 times speed up with this predecoder model. Also, UC San Diego has observed up to an order of magnitude improvement in logical error rate with the predecoder by using the NVIDIA Ising decoding model. And they're using it for bivariate bicycle codes, in particular for the 144.12.12 code, if you know the gross codes. And so already today, the NVIDIA Ising decoding models are offering substantial improvements in both logical error rate and speed for real customers and partners across the ecosystem. And so with that, we introduce NVIDIA Ising, an open family of models for your calibration and decoding tasks. And we are very excited to see what you do with NVIDIA Ising. Again, being an open model, you can use it and customize it for your needs. We hope that by introducing open models, the first open models to the quantum computing community, we will see rapid acceleration towards quantum scale and quantum advantage. And this joins our already open platform for developing and operating hybrid quantum classical systems. So to learn more, I encourage you to take a click of this QR code and visit the NVIDIA Ising webpage shown here. We have many different opportunities for you to get started, everything from different get started workflows, tutorials. You can access the models on GitHub. You can train a predecoder, run a calibration agent, and you can also see all of the details in the different research papers that are linked to at the bottom of the slide. Happy World Quantum Day to all of you, and I look forward to your questions. Thank you.
Marcus Collins, this is live.
All right, thanks, Krista, for a great talk. We have a couple of questions from the audience. So the first one from the audience, how does NVIDIA plan to scale quantum computing from research into real-world applications?
Yeah, thanks, Jen, and thanks everyone for joining today, and happy World Quantum Day. Yeah, in terms of scaling from research to real practical use, it's all about scaling up. And for that, we need to deliver, as we even talked about today, open platforms, open tools, and capabilities to help move systems from today's qubits to tomorrow's quantum GPU supercomputers. And so the way we see enabling that scaling is through this type of work, right? For example, with the open models today that we've released as part of the Ising family of open models. These models enable people to jump in, right, fine tune for their qubit modalities and help create essentially, better qubits that will enable better and more compute. And so ultimately we want to help through system integration, through classical algorithms, classical AI models and tools. We want to bring that together to enable better qubits and more logical qubits to happen across the ecosystem.
Amazing, thank you. Next question from the audience. With NVIDIA Ising launching today and NVQLink expanding globally, what's the single biggest bottleneck left between where we are now and a scientifically useful quantum supercomputer by 2028?
Well, ultimately, today's qubits enable, on the order of thousands of operations. And when we think about practical quantum computing that's truly advantageous, we need to get to, 1 million, 10 million, 100 million operations. And so the biggest bottleneck today is really closing that gap, right? It's getting from the thousands of operations today to the hundreds of millions of operations of tomorrow. And that bottleneck is really about the logical qubits, right? So we need to create better and more logical qubits that, when those logical qubits become better, they can undergo more computation. So we want more compute available. That's better and more logical qubits. What we've announced today with the open models is really about just that, right? At the calibration level, it's about enabling better physical qubits that in turn can become a better logical qubit, together through quantum error correction. And then with better decoders, through the pre-decoder work that we've shared today as well, right, you can create then better logical qubits. And so ultimately, it's all about the logical qubits, having more and better logical qubits over time.
Amazing, thank you. Last question from the audience here. This is a question in regards to NVIDIA Ising decoding. Is it for surface code? With what code distances were these numbers benchmarked?
Yeah, so the NVIDIA Ising decoding models that we've released as part of the Ising family indeed have been created for the surface code, but they are amenable to other codes as well. In the numbers that we've shown today, these the decoders, the decoding models that we've shared, these have been really tuned and exhibited for distance 13 and distance 31. So these numbers relate to those two distances. But what's really neat about this model family and the pre-decoder model is that you can build it, essentially train it for one distance, and it's in fact applicable to other distances. There's a technical paper on the archive to support this work, and you can dig in there to see more of the details around the different distances, the performance at different distances, how the training was enabled, and how you also can jump in and tune and train your own model, either for a different distance or for the distances that we've already pre-trained here.
Great. There's actually a couple of more questions streaming in here, if you don't mind a few more, Krista.
Sure.
Do you think the future of quantum computing will be more about designing better hardware or about training systems that can adapt to imperfect hardware over time?
Well, I like to see it, really coming at it from two sides, right? I think we definitely want to continue to improve kind of that base hardware, if you will, right? The physical qubits themselves, how we operate those qubits. We want to continue to improve those base physical qubits because that means we're starting from, in some sense, an easier starting point, right? It's a better foundation, and then it becomes easier to scale up the quantum machine, right? In some sense, easier to build logical qubits from there. So the better the base, the better the starting point. But at the same time, right, scaling up is going to be all about integration and really system engineering. And that's where AI really comes to play as well, right? AI can start to become the control plane for the quantum computer. As mentioned in the talk today, right? These quantum workloads, right? In the system engineering context, they're essentially AI workloads, right? So we will have a mix of AI workloads with some algorithmic workloads that we bring together into a full system for quantum computing. So it's not only about the qubits, it's also about that full system engineering that now needs to happen to enable that, more and better compute that we want to see for practical quantum
Great.
advance.
Fantastic. A few more questions here. What do you think about the benefits of quantum simulation? What does it allow to explore? I think in this context, the questioner is asking about kind of the classical simulation of quantum systems.
Yeah, so when I think about quantum simulation, right, there's the classical simulation of quantum systems, and then there's also the application of quantum simulation as a workload for a quantum, for a quantum GPU supercomputer, and for a hybrid workload. So here, when we think about simulation in this context of even training the models that we've released today, in this context, we can use some of this simulation data to enable synthetic data generation, right? So when we simulate what might happen in quantum error correction, how noise may propagate through the system, right? These simulations provide data for training AI models across the stack, right? So here we've used a mixture of synthetic and experimental data to train the models released today in the area of calibration and decoding. But then, of course, there are regimes where we cannot fully simulate the quantum system. I mean, after all, this is why we want to build a quantum computer and ultimately have a quantum GPU supercomputer, right? If we could simulate everything in quantum mechanics that we wanted, we wouldn't need to be working on this this very important field. So naturally, there's many things we can't classically simulate in the quantum space, and that's where it becomes really interesting in terms of a workload for the quantum GPU supercomputer, right? Where we look at simulation in that context around things like quantum chemistry, things like material science. You want to find materials that have perhaps more exotic properties, superconductivity properties, for example. This can lead to capabilities in energy, potential energy breakthroughs, right? You want to understand, energies or dynamics of quantum in the space of quantum chemistry, and so, there. Of course, quantum simulation plays a huge role in the applications that we will continue to improve upon in the space of quantum computing.
Great. I think there's one last question in the queue here. Could you throw some light on how skills of present-day semiconductor design engineers might come in handy for the quantum journey?
Yeah, so there are many types of qubits that are looked at, and qubits in fact can play different roles, right? So there are cases where qubits can really help in interconnect and in networking and communication, right? Quantum networking, and there's other types of qubits that are a solid state qubit. Other types of qubits are more atomic based, right? So you have things like neutral atoms and ion traps. You have superconducting qubits and spin qubits. You have photonic qubits, many types of qubits. And so the role of silicon here and semiconductors, right, can really take on a variety, a variety of roles. It can be important in the design of some of these solid state qubits, of course, where different types of qubits can actually rely on more standard silicon processes. And so those types of qubits can build upon many of the learnings that we've had in semiconductors over the recent decades. But of course, we also have the role of classical computing within the quantum computer. And, here today, we're talking about AI models that are trained and deployed on GPUs. And so again, right, we actually have a very hybrid machine, right? It's a hybrid system where we have the role of both classical compute and quantum computing coming together. And those two roles are actually incredibly critical, right? To stabilize and run our quantum computer, we need to have that classical, classical compute capability tightly integrated with the quantum computer. And that's where a real-time host with GPUs is really critical to enable running and deploying a quantum computer in real time and ultimately at scale.
Great. Thanks again, Krista, for an amazing talk. Thank you to the audience for tuning in, and I encourage everyone to tune into the next session as well.
Thank you, everyone.
All right, thank you so much, everybody, for joining me. Let me see if I can get this chat on screen here. But, so I could stream this for 1 hour, but let me put a link somewhere in chat so that you guys can, check it out if you wanted to. Let's see here. And I apologize, I did not get too much sleep, unfortunately. So I'm a little bit out of it, but very excited about what the day is going to bring. We could potentially see Spud come out, which is, OpenAI's a new model. So just give me 1 second to kind of get my bearings here and get chat up on screen, and then we're going to rock and roll. All right. And an aura for my dome. Yes, I need to change this thing because I put it back there, and then I think Elon has the same thing in his streams. DJ JJ, I need to sleep too. It's 2 a.m. Where are you listening from, and where is everybody coming in from? Let me know where you guys are from. I think somebody said they're from North Africa. Where's everybody else joining in from? And what do you think about NVIDIA's Ising? So I guess it's some sort of a new quantum approach. I think Jensen's going to be doing some cool stuff, doing a lot of interviews talking about it. Oh, yeah, let me give the link in case people want to go and check it out. Oh. So link is going to be in the description, and I'll post it here as well. Revelation glitch coming out of Russia. We got Seattle, Turkey, Kentucky, Romania, Toronto, East Coast, Spain, Bucharest, Swiss Cheeseland, Houston, Texas, UK, Argentina, Stockholm, Illinois. Sweet. Wow. Yeah, we got a really international community here. This is phenomenal. Poland, Very, very cool. Denmark. Very, very awesome. So let me just pin this one. For people that want to continue watching the NVIDIA stream, they can do so at that link. And, you know, this is not sponsored or anything like that. I just wanted to see it. I do have a contact at NVIDIA that kind of just lets me know when new things are coming out. This was kind of flagged to me. So we'll see kind of like what a big deal this is. Pretty interesting. I just don't know too much about the quantum stuff. So Fisher Deck is saying quantum is so overhyped. Yeah, it's like one of those things where it's like, what are the actual sort of practical applications? Because it seems like such a cool technology, but like, how do we actually use it? Like, what is it actually going to be sort of useful for? I need to be able to window capture. That's what I need to do. Yes, I did it. There we go. I'm extremely proud of myself for being able to put chat up on the screen. This is terrific. There we go. All right. So let me pull up Twitter and let's see kind of what's happening. So basically, to all that missed it, Sam Altman's house got attacked twice in the last several days. Everyone got arrested, I think same day. One person apparently threw a Molotov cocktail. Pro streamer, that's right. It only takes me about an hour to figure out how to get chat up on the screen. This is professional. Do not attempt it. Besides that, you know, we got Google DeepMind rolling out with some pretty cool stuff here. They're doing some sort of a robotic. Let me see if it's open source or not. It would be very, very interesting if it's open source. So they're rolling out some sort of an upgrades designed to help robots reason about the physical world. So that's Gemini Robotics ER 1.6. Yeah, Sam is going to invest in robo bodyguards. Yeah, but apparently, yeah, he's got security over there at the house. So they were able to, you know, put out the fires or whatever. So he's safe. And a lot of people are wondering now, like, is it, and I'm curious what everybody, actually, let me do a poll before I talk too much about it, just to kind of have a gauge for what you all think. Do you think that the AI safety community, based on how they're talking about the risks, the X risk from AI and AI alignment, do you think they are kind of triggering people? And I don't want to say they're pushing it towards violence, but is the rhetoric causing some people to get violent? How do I even phrase that? So does AI safety rhetoric violence? I don't know how to phrase that very well. So I know this is probably very third poll. Is this my job now? Yes, this is what we do on this channel. You just sit there and answer polls. This is yeah, basically all there is to it. No, I'm curious to know kind of what people think. Yes, okay, so everybody okay, no, it's going up and down. Let's give it a minute. is the rhetoric causing it or is the reality causing it? Yeah, I mean, I'm trying to ask the question in just like the most unbiased way possible. I think that's impossible. You know, it's very, very difficult. I'm just curious what people think. So, I mean, you know, I've talked to people from that community. They all are very smart, rational people. I haven't heard any of them call for violence or anything like that. They're very civilized, very rational people. For the most part, as far as I can tell. But, I mean, if you're saying that, you know, there's definitely going to be a high X risk, is that going to get some percentage of the people to, you know, try to do something about it? So cause violence against individuals like Sam Altman? Or I didn't follow the live. When will you do a recap? Was it important? I think I'm gonna need to. So this is, since they're talking about like quantum stuff and quantum GPUs or Q processing units, QPUs or whatever. I would have to read up on it to do a actual sort of a recap. So I'm probably not going to be doing a recap live. But maybe, you know, once I have a chance to read up what people are saying and catch up a little bit, then we can do a recap. Looks like Jensen's going to be on Dwarkesh Patel podcast tomorrow, so maybe they'll do a good job of kind of explaining what this is and what we can expect. I kind of feel like we were supposed to get the Spud model today. I know it's just rumors, but if they come out, that would be very, very interesting to see. Hint, let's see. Example for rhetoric. So yeah, okay, so the question, I apologize. So right now we're sitting at about 50-50. That was not a well-phrased question, because I didn't, when I say, is it the rhetoric, it sort of implies that they're saying something. I didn't mean to say that. Because again, from the people that I've talked to, some of the people that we've interviewed, again, very, very civilized people that do not call for violence or anything like that. And I'm not trying to push it one way or the other, just kind of trying to understand where people are on that sort of, on which side of the fence, so to speak. Do we have sources for those rumors? You know, what happens is like the OpenAI employees start their vague posting, right? So they kind of like, I don't know, there seems to be like a buzz that happens prior to the release of models, and all labs kind of do it. They kind of hint at it. So usually we see something. And we've been seeing that recently. So that's why I think a lot of people are thinking that today will be it. So it is possible that within the next, let's say, 2 hours, we'll see something. But that's obviously not guaranteed. What does everybody think about? I'm almost scared to do another poll now. People are complaining, like, how many polls are we going to do? So yeah, feel free to ignore the polls if that's not your thing. So I'm curious, who is a bigger winner from AI, is it Amazon or Google? Or let's say who will be? Are there any other? I'm actually right now curious, sort of between those two, Amazon and Google. Who will ride the AI wave better? Because both of them own quite a bit of equity in, for example, Anthropic. I think both of them own a chunk of SpaceX. I know Google is. I'm pretty sure Amazon does too. So they're going to have some very good companies under their belt. And yeah, so today there was a few announcements. AWS, Amazon, purchasing a bunch of stuff. They're really looking at AI adoption. That's Amazon, so it's going to be interesting to see kind of where they go with that. I think Google is very good, very well positioned to win because they basically going to own a lot of the things across the board, right? So they have the hardware, they have the models, they have the the reach. And will Pentagon walk back and start using cloud again? 100%. Or I mean, they're strongly going to try, because I've been trying to use the OpenAI models for OpenClaw and stuff like that. It's just not the same. They're good models, but Claude's my special boy. I don't know, something about it. It's like it just gets stuff better. Google will win everything. Demis better be nice. I got his new book. I got to start reading it. The Infinity Machine, or is it the Imagine? Yeah, I think it's the Infinity Machine. Would be very, very interesting to read. What agents is everybody running right now? So I'm sure most people have tried. Wow, Google 91%. You guys are saying 91% Google is going to be the winner. Okay, that's interesting. I'm clotting it right now on the other monitor. It's so funny because I have 3 monitors, and this one on my left, it's it's my mini PC that I've attached, and it's just it's OpenClaw, and eventually I'm also going to install. So I before this I was putting together. I installed Hermes from Noose Research, so I'm going to be testing that one out. I want to mess around with. I want to try to get Gemma 4, the newest Gemma, working on OpenClaw or on one of those agentic harnesses. Poll, has China already exfiltrated Mythos? That's such an interesting thing. I feel like, I mean, that's gonna happen. At some point they're gonna grab one of these models and just run. Or they're going to attempt to, right? So I think multiple people got arrested for trying to sneak some stuff out. How do you say Claude in Mandarin, I wonder? Hermes is better than OpenClaw. That's interesting. Okay, I really got to put more. I wish I had more time to do all of this stuff. Claude-san in Japanese. I wish I had more time to just like mess around with all this stuff, because it's so interesting, and it's like it feels like you have to run as fast as you can just to stay in place. All right, so yeah, most people are saying Google is the clear winner. All right. I'm still hoping that we're going to see some new models today. Hermes Agent version 0.9 just dropped, so it's a complete everything release. I'm going to take a look at that. And is Kilo AI... So Kilo AI has Kilo Claw. And it's actually a very interesting company. They got some real brain power behind it with very experienced founders. And I messed around with Kilo Claw. So it's their version of OpenClaw. Well, it is OpenClaw running on their system. Very safe. And so that to me is a very interesting approach to run some of the more sort of riskier stuff that I would want to test out. Are there any companies that you have your eyes on to invest in? Here's the thing. I strongly believe that the next big thing is space. As Fisher is saying, SpaceX plans to send satellites to do compute in space for AI. That's the next big wave. And I think the people that know what they're doing, they're placing their bets right now on those companies. Which ones? I mean, I have no idea. I'm not the tech investor guy, but I'm trying to get some people on the podcast to talk about it. There's well, I'm at some point I might talk about some specific ones that are very interesting to me specifically. So basically, SpaceX, absolutely. Rocket Lab, is that the one in Irvine? I grew up in Irvine, California. It's such a crazy place. It's a very chill place, but man, there's so much concentration of stuff there. Is Rocket Lab the one in Irvine? What's the rocket company in Irvine? If anybody knows off the top of their head, is it Rocket Lab? I think so. I think that's the one. There is what we're talking about. We're talking about a lot of different stuff, but I guess right now we're talking maybe where to invest, and this is not investment advice. There's a number of companies in Irvine that are like really interesting, surprisingly. Marvel Technology is another one that might be interesting for people to look into. Isn't Peter Diamandis involved with that? With which one? I mean, I feel like he's in everything, right? Because he's yeah, he's like a super investor, right? I mean, that's how. I mean, I'm sure he knows what he's talking about. I feel like he's got his, he's a major investor in a lot of this stuff. Or are you talking specifically one of the companies that we've mentioned, either Marvel Technologies or Rocket Lab? Because basically, here's the thing. Oh, okay, yes, you're right. So Peter Diamandis, I'm sure I'm mispronouncing his last name. I know the person very well. I've listened to a lot of his podcasts. Rocket Lab, boom. But yeah, so space robotics. So basically, in order to take these AI data centers to space, Google did their Sun Catcher project, and basically it's surprisingly viable. It's surprisingly viable in terms of like a lot of different things. They're able to create these constellations of satellites in space they're able to pass information through space lasers as long as they stay in this kind of tight formations. Yeah, he does his Moonshots podcast 2 or 3 times a week. I wish they did like segments, like clips. You know what I mean? Because sometimes they kind of like meander for a while, but there's a lot of like good stuff in the center. I feel like they had clips with just like the most important stuff. That would be absolutely, absolutely incredible. When are we going to get a good OpenClaw? I feel like very soon. And I know KiloClaw. Yeah, what does everybody think of KiloClaw? KiloClaw was interesting. I messed around with it. A lot of different models. Very safe. The people behind it are, I guess they're GitLab, or not GitHub, or GitLab, one of those founders of one of those companies, and now they're starting this. I think they have like 1.5 million users. So they're doing very, very well. So basically the key components of putting data centers in space, I mean, really what we're waiting for is SpaceX and Elon Musk to continue making delivery to a low Earth orbit cheaper and cheaper and cheaper. So they're sort of expecting that to be on par with building terrestrial data centers, with power plants here on the planet. So basically, per dollar electricity, whatever per unit price of building them in space is going to be roughly the same as on Earth by 2035, according to Google. So that's the whole thing. So Tech Ninja 420, the whole heat dissipation in space is a problem. So that's the one thing that I'm a little bit confused about, because there seems to be a lot of people say it's like a huge problem. At the same time, I don't know if anything if they've addressed it in Google. In their thing, it seems like they're not seeing it as a major stumbling block. So I wonder why. And I don't know the answer to that. But basically, in order to put those things in space, you're going to need tons of companies that produce everything that is needed to do that. So, for example, various laser equipment pieces, whatever they're called, like the light bulbs or the lasers, the actual transmitting devices, because there's probably random stuff that's being produced for terrestrial use. But I'm sure there's not companies that are completely sort of like really fleshed out the whole process for manufacturing stuff for space. I assume Google's going to be shooting their TPUs up there, the tensor processing units. But there's going to be a million different things that is needed to kind of put all around it in order to be able to effectively put that stuff in space. And all of those companies initially are, it's going to be a gold rush, because, a lot of them are going to get bought out. A lot of them are going to make tons of money because of how limited supply is going to be. No licenses, building permits, no linking to grids, no state control. Space is the place to build if you have the capacity. Yeah, it's safer. And eventually, if we keep dumping heat into the atmosphere, if we need to keep 10xing how much energy is needed, eventually that comes to an end. I think Elon addressed heat dissipation with door cache. That's interesting. Yeah, because reading the Google paper, I don't recall if they said anything specific about it. I mean, yes, SpaceX has. Oh, yes, SpaceX today I think hit 10,000 satellites in orbit. A few weeks ago or months ago, I think at this point, I was outside of my house at night and just keep seeing these things just zoom past in the night sky, just one after the other, just on this like very straight path. I was kind of getting freaked out. Apparently, it's called a Starlink train. So when they launch a bunch of these satellites, in the beginning, they're very much in the same sort of trajectory. And after a while, they kind of like slowly go where they're supposed to be. But man, watching that thing was weird because it does look, it's like a train of satellites just going across the sky. It was wild, wild to see. Yes. So the only way to shed heat in a vacuum is through thermal radiation, emitting heat as infrared light into the void. Huh. And so that's why the International Space Station has those enormous accordion-like white panels sticking out of it. Those are ammonia-filled radiators designed with massive surface area to dump the low-temperature heat generated by the astronauts and their equipment. And for Starlink satellites, the chassis itself acts as the radiator to dump heat. So yeah, I feel like they have some solutions for it. It doesn't seem like that's going to be the stumbling block. Literally, the biggest sort of stumbling block that they're pointing to is we just need to get the sort of the price per kilogram to shoot stuff into a low Earth orbit down to a certain amount. I think it's $200 per kilo, I believe. Don't quote me on that, but I think, yeah. So who makes the radiators, right? So that's like the question is who makes the laser units, who makes the radiators, potentially who makes the software that can keep these constellations in space, because if they're transferring data through light, through lasers, as they get farther apart, like the rate of transfer drops off rapidly. So they have to stay within a certain formation. So if you think about it, like that's the next big wave. And I feel like the people that are placing their bets now, it's hard to tell, obviously, like when is that coming and who to invest in. I feel like they have solutions to that, and maybe they're just not allowed to talk about it, either Google or SpaceX, or because they're just kind of like, they're not saying that it's going to be a big stumbling block, which is a little bit sus, if you ask me. So let me see. I keep refreshing my Twitter just in case something drops. What are some other big news that have been on your mind recently? It looks like Unitree is beginning to ship the robots to globally at scale. So prepare to see some robots pretty soon. Should I start building radiators? I would not be against the idea of maybe doing something in the realm of like just maybe having a fund. I don't know anything about this stuff, but if you have like a fund that's basically investing and laying down the groundwork for the stuff that's coming. We might have a gentleman on the podcast that is doing something similar. and I think a lot of you might know who he is. So he is Nathan Lands. Do you guys know who Nathan Lands is? So he's on Twitter, he's on YouTube, and he's going to start investing in. So he's thinking more about, like, I think, data centers on the surface of this planet. But I think it's also would be very interesting to start thinking about, like, what do we invest in to enable all that stuff to go to space. Is this like a slow news day? What is happening? Am I crazy? Unitary bots for 100K a pop. Yeah. Yeah, fund, but yeah, I'm thinking having people maybe invest. I don't know how to do any of this stuff in terms of, like, how to organize this stuff, but I feel like I know people that, for example, know a lot about the technology, specifically when it comes to space and all of that stuff. You know, if we're able to connect the people that know how to do stuff with the capital, the investors, the venture capital, or whatever, and maybe also talk about on the channel, kind of show people what's happening, I think it might be very interesting, because we're already seeing how a lot of this AI progress, the need to expand data centers, the need to expand how much energy we can produce. I mean, these tech companies are already solving a lot of problems that before nobody was working on. Like, we get better water treatment facilities now that are coming out. We get better, electricity production, etc., etc., etc. And I think that's just beginning. All right. Who's going to the Google I/O in May? That's coming up very, very soon. I know the second I sign off, because I've been on the stream for a while now. It's been a couple hours now, right? I think the second I sign off, I know OpenAI is going to be like, release the SPUD. Like, they're waiting for me to. They're waiting for me to sign off, and then they're going to release everything, release the Kraken all at once. That's how it works. I know it. But I am kind of falling asleep just a little bit. Do I go to, so I'm trying to start going to more of this stuff, to try to kind of get out there and meet people and just kind of hang out. Because as much as I enjoy kind of being a hermit and all that, it's probably important for me to get out there and meet people and sign off and on again. Well, everybody, that's all for me, and let's sign off for today. Did they release it? I'm back. Did we fool them? Let's see if they released the model. We might have fooled them. Wouldn't it be funny if it just like literally like released right now? That would be insane. Spud is out. Yeah. Well, he posted a video recently within the last hour, what Codex unlocks for Wasmer, which is a company, I assume. And I think Google DeepMind also posted something recently. Release the Kraken, yeah. I wish they would. Okay. One thing that they are talking about today is OpenAI is releasing a lot of like documents and notes that are getting leaked. So I wanna spend more time with Karpathy's LLM wiki and auto research nano. What was the original one? Nano LLM or whatever it's called. I do want to spend more time there and do some videos around it. It's very, very interesting. So we believe that OpenAI, you know, what we think it might be coming out today, we think that OpenAI is getting ready to release something big, likely this week, maybe today. So they're kind of been hinting at it. So they've been talking about the super app. They've been talking about Spud, whatever that is, right? Their next big model. Some people are even saying that potentially some sort of an image model. So we have no idea, but I feel like just at some point, as soon as they log off, they're gonna like release it. They're just sitting there, just waiting. As soon as I get off the stream, they're gonna release the model, because that's how it works. That's how they do me. Anyways, I might have to do another live stream if they do. We'll see. What is the super app? So I don't know. Yes, I know auto research is different than the wiki. I'm saying I want to catch up on all of the projects by Karpathy. So my understanding is Karpathy's wiki is like a research agent, like it's like a second brain that he did with LLMs, and the auto researcher is kind of like this automated approach to testing, so you can apply it to machine learning, or I mean pretty much anything where you can sort of have an outcome that you can easily test. Like, is it better? Is it worse? What is the super app? We have no idea. So maybe it's some, you know what? I guess it makes sense that they're talking about potentially releasing a image model, because then that makes sense as part of the super app, right? So the super app would have everything all in one, right? So you just talk to it and it will produce images and text and code and whatever. But I don't know if anybody talked about exactly what it is. So, what was I saying? Yes, so OpenAI is releasing some documents talking about basically, I think a lot of it has to do with that Anthropic did not buy enough GPUs. And when Dario was on the Dwarkesh Patel podcast, I think it was a couple of months ago, it was funny because I was like listening to that part yesterday or 2 days ago, and then that exact part started popping up on X, because they're saying, like, if you think that we're building this country of geniuses in a data center, it doesn't seem like you're buying enough GPUs to really like take advantage of that. And Dario was saying like, oh, they're being responsible, whereas some other people are not being responsible. They're buying too much. And now it might seem like, what if they just didn't buy enough? Is that why they're kicking people off of, OpenClaw? You can't use OpenClaw with the, max plan with Claude. Is that why some of this stuff is just not behaving as well? Some people are saying that, Claude got nerfed. Anybody had any experience with that? Did you see a rapid drop off with Claude? Can you talk about the unusable 5.4 or 4.6 on OpenClaw and solutions? So that's a good question. By the way, if anybody knows solutions, post them in chat. So my thing right now is I'm trying to branch out and test out different stuff. So this morning I installed Hermes, and I'm going to be messing around with that. I've also tested out Kilo Claw, and that's an interesting thing. You have to, it's a subscription, but there's certain use cases where it might be very, very good. And somebody mentioned one other one that I think we need to maybe take a look at. What was the other one that people were mentioning that is good? Sort of like as an agentic harness. But basically, and also it seems like, for example, Google is coming up with something that they're probably going to unveil at the Google I/O that is something like that. It's got some sort of a agentic functionality. I feel like everybody's building their own OpenClaw or some version of that. Yeah, I was using GPT, whatever, 5.4, I think, Codex. And I asked it to just research and give me some bullet points for Hermes agent, just so I can kind of start thinking about it, like what I'm going to talk about. And it wrote up this whole thing, and I'm looking at it, I'm like, this is just nonsense. This is just made up. And let me pull it up. I'll tell you exactly what it said. I could not believe it, because I asked it, okay, so what sources did you use for this? Right? Because usually when I ask for that stuff, it goes online, it does its resources, it puts it all together into one thing. It goes, it just goes, no, none. It wasn't source backed. I wrote that one from synthesis and product framing, not from using any of the documents. And I was like, what are you talking about? Like, what do you mean? Like, because for however many months OpenClaw's been out, it's been so good at doing the research, mostly through Claude 4.5, then 4.6. And now it literally just hallucinates a bunch of crap that's not rooted in reality in any way. It's like, here. And when you ask it, it's like, yeah, I just made that up. And this is somehow like, what is happening? It's so bizarre. Yeah, Entity Steel is saying, I think all the big AI companies are rerouting compute right now. Yeah, somebody had a long explanation on X, basically why this might be happening in terms of like if during peak hours. And actually, now I think about it, that happened during probably the evening peak times. Exactly. So if it gets rerouted, it causes issues. But man, it's incredibly frustrating right now. But it kind of shows you how not enough compute we have, as how much more we need, so to speak. Let me get this out of here. So some people mentioned some open source models that are working very, very well. So GLM 5.1 is really good in OpenClaw. What do people use in Hermes? Aside from the well-known big models, could you do a poll on how many tokens people use? Yes. What should the categories be, or the sort of the ranges? How many options can I have on here? So I can have 4 options. So so let's guess. I guess let's do like per week or per month. Let's have people estimate how many tokens they burn through in any given month. And I'm actually curious myself because, unfortunately, yeah, I lost a bunch of money because I forgot to switch from the... I was trying to see how much it would cost to run it as an API, and I forgot to switch it back. And when I checked back again, I burned through a lot of money. It was very, very sad. All right, so like less than 100,000, 100,000 to 300. And yes, that's, let me see. But recently, like for me, it really went down. Just because just recently it's just not as fun, I guess. Because yeah, you got to think either, because you have to settle for not the model that you want to use, or you have to, you know, use something else. So I've been going at, I think, 17 million per day, and it dropped off towards in the last few weeks. March 2026. Like 500 million, I think. But that's just that's just the API, I think. When I first started 2 years ago, 3,500. So is that per month? Yeah, I think it's showing that I did 500 million, but I don't know if that's so total tokens in 437 million something 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 something. But you know, if you're looking at the API, that's the API. That's not. Where do you even see if you're using Claw code? Does it show you how many tokens you're using? Oh, it does. Okay. All right. Itangalo disconnecting. Cheers, everyone. Cheers. Thank you for joining us. I'm probably going to be hopping off pretty soon, too. So I honestly don't know how to track. How do you track Cloud Code usage, the free usage, so to speak, right? Because you're able to see the API cost. Because that's the API. That's the API usage, but it's got to be more than that if you're looking at. Yeah, that doesn't show Claude code. That is strictly API. Anyways. Let's see how much people use. Yeah, I don't think they show it anywhere. So is this a good estimate? So let's say like less than 500K. Less than a billion, less than 10 billion. Yeah. So less than. Yeah, I'm just going to do exactly what you put there. Yeah. I feel like most, well, I'm just going to put this. We can always change it if that's the wrong units or whatever. If that doesn't show us the distribution properly, but anyways. Oh, okay. So Fisher deck, you're saying you're routing everything through Codex, and Codex shows exactly how much you're sort of using. Yeah, I guess I don't know exactly how much I've been using because I'm not able to get the tokens from the Claude Max subscription. So it's got to be a lot more than that, I guess. All right. Well, I am kind of fading out here, so I think I need to take a break. It's been a wonderful. Adam GPT just posted. Oh no, he's welcoming a new team member. Yeah, it's like literally every OpenAI employee posted within the last hour. Chris, GPT-21, I think Rune posted. And then Adam GPT, who works for OpenAI, posted, they're just waiting. They're just waiting. They're going to launch it as soon as we close this. I know they're waiting for me to get off this live stream so they can launch the biggest thing ever. Anyways. Yeah, people that are saying these very, very large numbers of tokens used, where's most of that going? What are you building? Is it building specific apps, or is it just doing stuff like agentic stuff, like doing research or whatever? Like, where's that going? So half of the people are saying less than 1 billion. The other thing that they were saying, Boris Chorny, he was saying that, for OpenCloud and stuff like that, they don't use the cache features very well. So they're just, so apparently, yeah, I should just log off so that they can release the SPUD model. They're gonna release it. I hate this. Anyways, yeah, because like a bunch of OpenAI employees are posting stuff. Whatever. I guess, yeah, let's release the Kraken. Oh, people using your apps is the biggest token usage. Oh, okay. I didn't even think about that. Yeah, but yeah, if you're building apps and then you're for the public and it uses tokens, then yeah, people would burn through unlimited amounts of that. That certainly makes sense. What are they releasing? Well, maybe nothing. Rumors are that they're releasing something big, maybe the super app that they've been talking about, maybe the SPUD model, maybe nothing. Maybe, yeah, I wouldn't like bet on it in a sense that like it's not guaranteed. Nobody confirmed anything, but just the amount of chatter that there's been around this new release, you'd feel like they dropped something. Claude just released within the last 10 minutes routines in Claude code. So that's interesting, but you know how every time Claude or Anthropic release something, like it just destroys stocks of a certain industry, right? It's like cybersecurity, all the stocks are down. So they just released routines. So I wonder what stocks are going to crash because they released this. I'm curious. If you can predict, if you can just short the market based on what Anthropic has been releasing, I feel like you would have done very well over the last however many months. ChatGPT taking a while to load. Interesting. Oh. Yeah, they're gonna release something. Anyways, thank you so much for everyone for joining me. This was very, very fun. I hope you enjoyed the NVIDIA thing. I hope this was fun. I appreciate everybody joining me here and hanging out. I'm gonna log off and rest. Well, and then come back and continue with my Hermes, messing around with Hermes agents, which I just set up. I missed it last time. Did anybody say which model they prefer in Hermes? Like, is there some setup that is just sort of the best? If I'm just beginning to test it out, 5.4 is unusable. GLM 5.1 is good in OpenClaw. I mean, I'm in the States, so the time for me is like early, morning. But yeah. Anyways, thanks everybody for joining me. You guys have been awesome. I'll try to do more of these because they are very, very fun to do. So thank you so much, and I will talk to you soon. And yeah, see how they post the next big model, like right after this. Right after this. I'm pretty certain of it. Bye.